All right, so we're starting with number 2 here. We got this bullet traveling at this, penetrates the block of wood and emerges on the other side. And the block is stationary beforehand on a frictionless surface. And how fast does it move after the bullet emerges? So one of the first questions to ask yourself, do I have a system here? And if so, what are the objects in my system? So do I have a system here? Yes. What are my objects in the system? The bullet and the block of wood. So, is there, with the system, is there a before and an after? Yes. So you must include a momentum diagram in your Y. Because there's a system and there's a before and after, you have to include it. Alright? And then, so now you also, then you look at your Y and say, okay, well, let's see what I know because there is a system. So, it's number 2. I know that probably a good idea to show off that I know what momentum is. Momentum is inertia in motion, right, or however you want to say that. You should probably also make sure that people they understand that the bullet and the block are a system. That's important because if I don't look at the whole system, I can't have the momentum being conserved. So it's important that I identify and point out that I know what the system is. Because then I need to make sure I express that momentum is conserved in the system. All right? Anything else? Can you guys think of anything else I need to state there? Make sure that my reader knows I know. That's about it. I need to do my diagram. How many objects before the interaction in my system? 2, the bullet and the block. How many objects after my interaction? Still 2. You're right, in a lot of the other ones there's only 1. Like the one right after this. I believe the bullet stays in the block. Right? This one the bullet goes through the block, so there's 2 before and 2 after. So I'm going to draw that. Let's see. I'll have my bullet and I'll have my block. And beforehand, make sure these are momentum vectors. We'll call that, whoops. The momentum, and I did it again. Wow, welcome to Friday. The momentum of the bullet, that's beforehand. And we got the what's the momentum of the block beforehand? Nothing. I'm going to call my block L. Because I don't want to call it B. Why don't I want to call it B? Because the bullet's B. And then afterwards, I've got this block. Actually has this little hole in the middle of it now. And that would be that's one of the simplifications. They didn't talk about that the bullet like pushed any of the wood out of the block or something. Now, I'm going to say that my block, and I noticed I put a prime on there to indicate, it didn't really come out well. Let me do that. I put a prime on there to indicate that it's a different momentum than that first one. And my bullet now has a different momentum also, so I'm going to put a prime up there. Remember, that's just a different way to indicate, a different value. Same thing, momentum, but the prime indicates a second value. What do you think double prime would indicate? another one, and you can keep going up there. Okay, just like you'd put, like 1, 2, 3, or A, B, C. It's just a different way of noting it. Those of you, can't remember, do we have anyone in here in calculus? Or pre-calc? You're in calculus? Do you guys use the primes at all when doing like derivatives and stuff? Just another way to indicate. Okay. Just always trying to find out what they also do there. So, that would be the expected diagram. Remember, those end up being 40% of your Y grade. All right, so let's start off here on the how. And I start off with my big fact that momentum is conserved in the system. So from my equation sheet, I have the momentum of the system. Remember, it's a vector. Equals the momentum of the system afterwards. And that's why I use that prime there again. So that's directly off the equation sheet. And then as Bob told us, and he's completely correct, 2 objects before, 2 objects after. I like to recognize that because then I say, okay, so before, I'm going to have 2 momentums here. And of course, they're going to be added together. One of them is going to be of the bullet. And one of them is going to be of the block. And then afterwards, I'm also going to have 2 momentums. One for the bullet and another one for the block. And I like to just look at my diagram, 2 objects, 2 momentum. 2 objects, 2 momentum. Kind of keeps me so I don't by accident forget one or add an extra thing in there or something like that. And now let's see. So, inertia of the bullet, velocity of the bullet beforehand, plus momentum of the block, which was 0, equals inertia of the bullet, velocity of the bullet afterwards, prime in there again, plus inertia of the block, velocity of the block afterwards. Everyone knows how I got replaced P with MV. Which M? There's 2, 3, F2 up there. M sub B, which is for the bullet, and M sub L, which is for the block. Yep. All right, so now I just substitute in values, right? Inertia of my bullet, 0.013 kilograms. Well, what did I do there? I converted grams to kilograms, just like you guys did yesterday, or the day before, I can't remember, I saw it yesterday. And its velocity ahead of time is 213 meters per second. I'm going to assume it's in the positive direction. So 213 meters per second. I'm going to get rid of my 0 because who cares about it. Mass of my bullet, 0.013 kilograms. Velocity of the bullet afterwards. Excuse me, for me it's 150 meters per second. I've run out of room, plus the inertia of my block, 2 kilograms, and the velocity of my block afterwards, which I don't know, because it's always good to have one variable, right? And then solve for the velocity of the block afterwards. You have all numbers in one variable. Give it a try. Give the math a try. If you need help on it, give me a yell, and I'll come over and see where you need help with the algebra. Alrighty. So we're going to go on to number 5, and I asked myself the same 2 questions again. Is there a system My answer is yes. And what are the objects in my system? The two ice skates. Why not the frozen pond? Okay. And also, what's our goal with ice skating? Why bother doing it? Huh? To get rid of friction, and so that they become a system. You know, if this was two people are standing in the classroom, they're not a system. They're not a system without the earth. But here, we put them on ice skates. There's no friction to connect them to the pond, so the ice skaters are the system by themselves. All right. So that is important to show in your why. And then this is very similar, I think, to the carts that some of you did yesterday, right? The exploding carts, that lab. This is kind of the same idea. So in my why here for number 5, let's see. I'm going to have my good old standbys. Momentum is ... 2. You can tell I've done a lot of these today. Ice skaters are the system. Momentum is conserved. ... I might mention that those two are the system because they don't have any friction to tie them to the pond. You know, that could be another good thing to have in that Y there. And then let's draw our picture. Let's see. We'll go really artistic on this. If they're just standing there, how much is their momentum together ahead of time? 0. And they're actually, I'd say they're one body ahead of time, and how many afterwards? So over here, then we have, do they classify them at all? Do they say a boy and a girl, or do they say skater 1 and the other skater? Skater and dater. Thank you, gentlemen, for getting that reference. We're going to call this one dater. And this one skater. And they would have momentums in the opposite directions of each other. There you go. There's a nice complete Y for you. Skater is going to the left, dater is going to the right. It's the letter D for dater. So it's called a subscript, by the way. Same equation. And so beforehand, I don't have any. That's easy. Afterwards, I have two objects. I have the momentum of the skater plus the momentum of the dater. And notice that they're both vectors, right? Which direction do you guys want to call negative? To the... Yeah, but they were a different object together. So I could have the notches or just leave it off. I didn't hear. I heard to the right. Ryan, you decide. I've heard one either way. To the right is negative. So I'm going to have 0 equals momentum of the skater minus or plus a negative momentum of the dater. So that tells me that the momentum of the skater must equal the momentum of the dater. A little tricky math there. Inertia of the skater, speed of the skater, inertia of the dater, speed of the data. I've already taken into account my direction, so that's why these are just values, just speeds. And let's see, what do we have? 48 for the skater, 0.64, and then the data is 0.82. Ooh, so which one do I think is more massive? The one that goes at 0.64 or the one that goes at 0.82? More massive. 0.64. Doesn't matter. Ryan, if you ran into me, who's going to move more? Because you have less inertia, less resistance to changes in motion. So these two are going to push off each other. They're going to have equal but opposite momentums. The one with less inertia is going to have to move at a faster rate to be able to do that. So the faster one must be the less massive one, the less inertia. That's just a kind of, it's a good way to think to help make sense of it, but it takes a while to get there. So, what did we say the inertia of this one was? 48. So I have 48 kilograms moving at 0.64 meters per second equals the inertia of the data, which I don't know what that is, and moving up 0.82. And then do the math and find the inertia of the data, which we're expecting to be less than, but not too much less than, 48. My gut is telling me something around 45 probably will be the order of the day. Give it a try, see if you get it.